Hello, my name is Eric Mitchell, and today I'll be presenting our work, Offline Meta Reinforcement Learning with Advantage Weighting. First, what is meta reinforcement learning, or meta-RL, and why do we care about it? In the standard meta-RL problem setting, an agent is able to interact with several related training environments in order to learn a prior that enables rapid adaptation to a new task during the meta testing phase. Past work has shown that agents can indeed rapidly adapt to new environments with a very small amount of experience. For example, learning to manipulate a new object with only a few trials. However, meta training typically requires a significant amount of data collection in the environments, which can be costly. So in our paper, we introduce the offline meta-RL setting and ask the question, can we learn new tasks rapidly without needing to collect a significant amount of data during meta training? We can think of this offline meta-RL setting as similar to the pre-training and fine-tuning paradigm used in supervised learning. The offline meta-RL setting brings with it several challenges. Some of these are inherited from offline RL. For example, the offline data might be suboptimal, and the value functions that we might learn on this offline data will be prone to extrapolation error. In addition, specific to the offline meta-RL setting, we typically will only acquire a small amount of offline data for the test tasks, which means that our algorithm needs to be intelligent in order to not overfit to this small amount of data. So what might an algorithm for this setting look like? Well, intuitively, we might start with an offline RL algorithm and then try to extend it to the offline meta-RL setting. For example, we might start with advantage-weighted regression, which is a relatively simple RL algorithm that is known to work well in the offline setting. And we might combine it with MAML, which meta-learns an initialization that can be rapidly adapted to new tasks with gradient descent. So this MAML plus AWR algorithm would learn the initialization to both a value function and a policy. And during adaptation, it would first adapt the value function using some data from the new task. And it would then use this adapted value function, along with more data from this new task, to adapt a policy. However, there are two issues that we identify with MAML plus AWR. First, the AWR policy update sometimes produces ambiguous updates, which causes the policy to fail to correctly infer what the task is. And second, in general, MAML's adaptation process, which is just gradient descent, is limited to relatively non-expressive rank 1 weight matrix updates. We find this slows and destabilizes meta-learning. So therefore, we introduce our algorithm meta-actor-critic with advantage weighting, or MACA. MACA provably solves both of these problems, first with an enriched policy update that avoids the ambiguous gradient problem, as well as with new what we call weight transform layers, which enable higher rank weight matrix updates with even with a single step of gradient descent. For more details about both the enriched policy loss and these weight transform layers, see the paper. Finally, we perform some experiments in order to better understand this algorithm. First, we ask the question, does MACA learn useful priors from offline data at all? We construct offline variants of common meta-RL benchmarks, and we compare with several sensible baselines. First, an offline version of Perl, a state-of-the-art meta-reinforcement learning algorithm, as well as an offline multitask reinforcement learning and fine-tuning baseline based on AWR, and as well as a meta-behavior cloning baseline. And we find that MACA provides the best performance in all of these environments. Second, we perform ablation studies to understand how MACA's performance differs from the more naive MAML plus AWR algorithm. We find that if we remove either of MACA's key components, the weight transform layers or the enriched policy loss or advantage head, we see significantly degraded performance and learning speed. So finally, our key takeaways. First, we've introduced the offline meta-RL setting, for which an algorithm can utilize the largest possible pool of training data, any pre-existing data, and is not required to collect any new data from these training environments. Second, we introduce an algorithm for this setting, MACA, which effectively learns useful priors that enable rapid adaptation to new tasks without any environment interaction at all. If you'd like to see more description of our method, more ablations, or discussion of hybrid offline-online settings, please see our paper. So thank you so much for your time. This was joint work with my wonderful collaborators, and if you'd like more information, again, see the paper or our project website below.